So this is me. This is my name. It's Dirkjan Bussink. Probably nobody except Dutch people can pronounce it. You can find me online, usually on that nickname, anywhere, Twitter, GitHub, whatever. What I'm doing, I'm an independent contractor, doing mostly performance work, security stuff for companies. And actually, one of the projects that I've been active on for a long time is Rubinius. Rubinius is a Ruby implementation, so basically, you can use it as an alternative to what you would use by default if you want to run a Ruby application or like a Rails application or anything like that. For example, there's also JRuby, which is also an alternative implementation running on the Java virtual machine. And one of the things we have that I think is cool is that we don't have a global interpreter lock, so you can actually have true concurrency in your application. So you can actually see your application use more than 100% your CPU. We have a better garbage collection. We have a generational garbage collection, which is actually something they're working for in Ruby 2.1. But we've had that for a long time. I've recently been working on a concurrent garbage collector, so you can your application can keep running your Ruby code while garbage collection is happening in the background. I'd like to give a shout out to Engine Yard. They actually sponsor the work I do on Rubinius. They have been sponsoring Rubinius for a long time. Brian Shirai works for them as well on Rubinius. And in the past, they had Evan Phoenix, the original creator of Rubinius, working on it. So I think they're very generous in doing that. So what I want to start with is basically where the idea of the myth came from. So for example, these are some random quotes. PHP too slow for Facebook, builds its own version. It's actually a headline that they had when Facebook announced they were working on hip-hop, which is a framework what they use to compile PHP code into C++. And they actually continued on another path. Right now they have something they call the hip-hop VM, which is a virtual machine they use. So that's one thing. Ruby, of course, has been notorious for performance. So everything you heard about Ruby being slow is not true. It's about twice as slow as that, which is something that in the past was true. Like Ruby 1.8 was actually a really slow implementation. It was really pretty naive in how it implemented stuff, which I'm going to talk about a bit about that. And actually, this is a quote. How JavaScript slows down the web, which is interesting, but this is actually from 2006. And JavaScript is an example of where where it was first very slow, started as something that they put into Netscape like last minute and never really did much with until it really started to pick up as the language you write your big parts of your web application on the client side in. So nowadays, like the whole idea about JavaScript is performance very different. So I got this quote from Shit Hacker News says, I often drop down to Node.js if I really want to be close to the metal. I find this quote hilarious because I think it's totally misses the point. But what I think is really interesting about it is that it shows a complete change of perception, that people actually think that if they write JavaScript, they're like close to the metal. What does it mean? Is it like, oh, I'm writing assembly code, or I'm really know what I'm doing? I'm considering my CPU cache performance and all that kind of stuff. Well, I don't think that's what this guy intends, but it shows that it's very different. So last time on Google I/O, somebody said like JavaScript performance. You know, this is a number like 100 times, which basically says nothing because it all depends on how you use it, what you use it for, and how it works on your application. But still, in general, they probably compared a bunch of benchmarks and said, OK, we got 100 times more performance in 7 years. And that's something I think that you can do with any dynamic language and really, really improve it and not have those issues where performance is really, really something that people feel like, oh, there's no way to make this fast. So what I want to talk quickly about is making some things clear, which is often something that people confuse. So up to now, I've been talking about dynamic languages, which are usually opposed to static languages. But there's actually also another axis of languages, which is called weakly versus strongly typed. That's actually not the same thing. So I'm going to talk a little bit about these 4 languages. So for example, if you take C, C is statically typed. So it means in your program, you have to define your types. So you say, this is an integer, this is a character pointer, this is whatever you're working with. But also it's weakly typed. What that means is that if your application runs, it doesn't actually really do much with that type information. In C, you can say, I'll cast a integer to a pointer. And, well, if you do it kind of in a right way, you can get away with it if you make sure that integer is stored somewhere and is actually a valid pointer. So all that kind of stuff you can do in C at runtime. There's no type checking at runtime in C. It all gets translated into assembly. It just runs it. It never checks anything again. So another example that's different is Java. Java is also some language. You have to define your types before you run it. But if you do some really weird stuff at runtime, you actually get proper exceptions, something like a class cast exception. If you have a Java class and you think, oh, this should be some other type, and you change it, and it actually is not that correct type, it raises an exception. It doesn't cause your whole program to crash, like how C would work. So it means it actually enforces those types at runtime and actually checks them. So next I'm moving to Ruby. Ruby is a dynamic language, so you don't have to define your types. You don't have to set that all up, but it's actually strongly typed. So it means in Ruby, you cannot say 1 plus a string, because it will throw an exception, because there's no valid operation that says how to add a number and a string in Ruby, for example. Compare it to PHP, where a lot of stuff like automatically changes and happens under the hood. So you can do really weird things where, well, it kind of sometimes makes it a string or maybe a number, or it can be very, very dynamic behavior, and that's because it's seen as weakly typed. So types do have some information, but types are not strictly enforced and stuff like that. What all these things have in common is that types are significant, and types are actually a really important thing and a really important concept in optimizing dynamic languages. So types is not something you can ignore in a dynamic language, but it's used in a very different way than often used in static languages. So that's a very basic setup for for my next topic, which is actually imagine yourself thinking, okay, I feel like I'm a good developer. I want a new challenge. I'm going to make my own little programming language. You know, I like dynamic languages, so I want to make a language that's also dynamic. So, yeah, you know, I don't want to have to specify types. I want to be really flexible, so things can change when your application is running. Like, I want to be fine. So you have to think about, okay, how does it mean? Like, how am I going to store information for my language? And there's a really easy structure that people use a lot, but it also has its downsides, which is what I call the lure of the hash table. So imagine like you're on your boat on a Greek island and you hear the siren sing, and it's like, oh, it sounds so nice, I'll go there. But you have to be very aware of what you're stepping into, because hash tables end up being in a lot of places in dynamic languages. So example, if you take a method table, this is a little piece of Ruby that says I have a method table, and I just use a hash internally to keep track of it, just to show the example. Okay, I want to be able to store a method. So if somebody defines a method in my program, I need to store the name of it and some piece of code that I can run with it. And at some other point, I need to find it back, because I need to run that code, because somebody calls a method. So I need to be able to say, okay, give me my method back, give me my piece of code, and I can run it for the person who's calling this certain method. So that's one example where you would use hash tables. Another example where you would use hash tables is instance variables. So this is, for example, a little snippet of Java code where you say, okay, I have all my instance variables defined, and I set them up in a constructor. Actually, if you look at how, like, this is not flexible if you want to have a language where you want to be able to add variables without having to always predefine them. So you think, okay, that means I need to have a structure that allows me to grow. So you might end up actually doing something like this. So I have a hash table with instance variables, and I store them. So if you would ever do this in a Java project, probably your coworker would like review this and say, what the hell are you doing there? That's like totally non-performant. That's totally dumb because you need to do a hash lookup on every instance variable I use. Like, why would you do that? So that actually shows what the problem would be if you do that in your own little dynamic language you're writing. So basically what it means is hash tables are everywhere in dynamic languages. And a lot of work on making dynamic languages fast is actually removing hash table overhead. It's a sometimes very dull and sometimes very basic work, and there's no big way to say, oh, we got to change this, and everything is 50% faster. No, the only way to do is chip away at everything. So basically, there's no way to do 50% at once, but you have to do 20 times 2%. So it's a lot of work, and it's a lot of small things, but the small things end up adding up. So first thing is one of the really basic techniques, and it's a very important technique to optimize things. It's called inline caching. And inline caching is a mechanism used for optimizing your method calls. I need something to drink. The air conditioning kind of killed my throat a bit, I guess. So inline caching, it's about method calls. So if you remember the method table we had before where we store our code, and what we don't want is every call, so every time we do something like this, we don't want to have to look it up in a hash table. So there's a very basic technique we can use here. It's a technique everybody should probably be familiar with, and that's basic caching. So actually what we do is we make sure we have a little extra room in our code. And what we do, because we need to store this name somewhere. So a technique in Rubinius we use is there's a place where we store the name, but actually what we do is we replace the name with a cache structure. And what we store in such a cache structure is very basically something like this. What we cache is, what is the type of P here? And we have some identifier for that. That's what we call the receiver class ID. It's an identifier that says P in this case is a person. But maybe P isn't set up like this before, but maybe P is created by, for example, constructing it somewhere else and giving it to a method that actually ends up calling names. So you don't know in your dynamic language, you don't know up front what the type of P is going to be, so you can't immediately say that. But what you can do is say, okay, if P is still a person the next time we call it, we just run the code directly. And that means we change our hash table lookup into a comparison to this identifier, which is a lot faster and a way shorter operation, and it runs way faster. So this kind of technique we can use to basically remove almost all of the overhead of calling a method, only having to check the types against each other. So there are, of course, places where the type changes every time. So if you have a structure where you use inheritance and stuff like that. So there are also techniques for improving those cases. But this is like the really basic case that we do. So that's for method tables. So the other example I gave was instance variables. And for instance variables, we use something different. And we call it like specific object layouts. So basically, if you look how an object looks like in memory, in Rubinius, it's very straightforward. An object has a header. It's almost the same thing on like the JVM. An object has a header, and a header has a bunch of flags. And flags are things for, it stores some state about an object. It stores, actually has a type identifier. If it's a type for the virtual machine, it has, I don't know, in Ruby you have things like an object can be frozen. So we have a bit in there that tracks if it's frozen. We use it for the garbage collection to store which kind of state we're in for the garbage collection when marking objects, all that kind of stuff. So we have headers. We also have a class pointer, so basically a pointer to say, okay, this is an object of this type. And we have a pointer for instance variables. So basically that's the layout for every object. But the trick we use is actually we create different layouts for different types of objects. So how do we do that? So we have, in Ruby, we have a compiler, which is actually, in Rubinius, it's also written in Ruby, so you can just run your compiler on your source code, and actually it tracks some state. So what it tracks is actually it sees, okay, what are the names of instance variables I encounter? So you have here attribute reader, but you can also have the notation where Ruby has an instance variable with the @ symbol in front of it. So we track what we see when we compile your code. So it means that the first time ever we create one of these address objects, we create a dedicated layout that says, except for those things I mentioned before, we create room for 3 extra more variables. In this case, for the street, the number, and the city. So we don't have to use a hash table for that. And what that means is actually we can translate bytecode instructions that say, I want to push this instance variable onto the stack. We can change them basically into an array style reference into this object. Like I want to have the value with like on the first offset. So that means we don't have to go into this lookup table and say, I want the value for number. So is there a number in this hash table? Okay, to hash the name and get it back. Oh, if there's nothing, we get nil. All that kind of stuff, all that overhead you can remove. So this kind of technique also like applies in Ruby, like to constants, because actually constants in Ruby are not constant. So you can actually change them at runtime, whatever you want. So you have to be able to have a lookup mechanism for that. You could do similar things for like global variables in Ruby. We don't do that at the moment because we don't want to encourage people to use global variables by making them very fast. But if people have really, really good use cases, we might be convinced of making them fast. So they're not fast at the moment. They're still a hash table, but we could improve that. So those are the things. Those are two like basic examples of moving hash table overhead. And they really, really help in improving our performance and actually making your whatever Rails application or something run a lot faster. So next I want to talk about a different technique, which is just-in-time compilation, which is actually usually what people get really excited about. Because actually what it does, it translates your code of your little language, in this case we use Ruby, into actual like assembly style machine code. So take, for example, I'm going to use this example to illustrate a few of those techniques we do. So take this very, very dumb piece of code, which basically said, I want to 100 times call this method. And this method actually calls another method and adds the value to, it returns to 1 and returns that value. So it's really, really basic, but it shows a bit of the things you can do. So the first thing is we can, there's 2 plus 1, which is actually a constant expression. So it's an expression that never changes and never does anything else. So we could change it from 2 plus 1 into 3, because that does not mean anything different. Another technique we could do is we could inline methods. Methods inlining means that we move the body of a piece from a certain method into another method, which means we remove the overhead of calling a method at all. So in this case, what we could do is say, okay, we are going to inline the code for method 2 into method 1. So it would change to, instead of 1 plus method 2, it would change into 1 plus 2 plus 1, which we can actually translate into the value 4. So if you look in Rubinius and see what assembly actually comes out if you do this, I've cut away a lot of setup stuff, so method setup. So if we call a Ruby method, we have to set up a lot of stuff and things like that. And actually what we see is there is actually only one line that's really significant here, which is the line that says the move instruction, move the literal value of 9 into the EAX register, and afterwards we jump to a return. And that's actually all this code translates into. So you might think, why is this value 9 there? Well, that's actually the way we store numbers in Rubinius. Because numbers are, like everything in Ruby is an object, so we have to be able to think of a way of how is an object different from a number. Or we would have to create actual objects to store numbers, which is a lot more extensive. That means for every number, you would have to allocate memory from your garbage collector, etc. So there's a very basic technique that says that comes from the idea that not every pointer is the same. If you have a 32-bit machine, pointers are always a 32-bit value. So that means the value 0 would be a valid pointer, even if it's a null pointer. The value 4 would be a valid pointer. The value 8 would be a valid pointer. But there's no way the value 1, for example, could be a valid pointer. So we kind of abuse that, which means that everything that ends with like a 1, so a bit set at the end, is actually a number represented by the other bits. So that means that if you translate that into this is that if you translate 4, so you have to move 4 1 bit, that means it becomes 8, and then you have to set the last bit to 1, which means it becomes 1. So actually this code completely removes these method calls, it completely removes the plus, and it just changes into immediately return this value, and we're done. So that's a thing that's a few things that a just-in-time compiler can do. It can inline methods, it can fold expressions together, it can propagate constant values into other places. So those are really basic techniques we can use there to speed up your code. So, oh yeah, sorry. This points at the line that's actually the meat of this optimization. So this stuff is all very, very interesting, maybe not, but what I think is important is that what it means for you as a developer if you work with dynamic languages. So what are the things that you should do if you want your dynamic language, like if you want to write JavaScript, if you want to write Ruby, if you want to write anything like that, what should you do to make sure that the implementation that's running can actually optimize your code well and you don't do stuff that actually really works against optimizations like this. So I'm calling it be nice. Be nice to your virtual machine, which means one big thing is write type stable code. So even though we don't work with a static language, if you look at it, if you run your application, types rarely change. So you should write code that does not change everything while it's running your code. There are actually like very big violators of this principle. Actually, I was looking into a performance issue with an application that was using the Haml templating language, for the people who know that. It's a templating language that, at least it's a Ruby implementation. I think there's maybe implementation for a few other languages. But it was really, really slow on Rubinius, and I was like wondering why is that? So I looked into it, and actually what Haml does, it actually creates new types, it redefines types on every template it renders. So it means that any of the optimizations that Rubinius would be doing would be thrown away the next time we would run it because it was all new and all different and all that kind of stuff. So there are still things, of course, in there that we could optimize better, but there's some fundamental issues there with how they write the code that makes it really hard and really complicated to optimize. The reason there is not only, the thing is that if you don't write type-stable code, even if you have one place in your application that affects it, that could have a much bigger effect than only that single place. So it could have an effect on other code performance in your application as well. So that's always something to be really, really careful about. So besides this, write simple and small methods. So this is not only a good idea from a maintenance perspective or a good idea from the idea of we want to write our code maintainable and we want to be able to change it easily. You know, a method should have a single purpose and not do 2 or 3 things at the same time. It's also very good for your performance because if you have small and simple methods, things like the just-in-time compiler can actually look at your code better and say, okay, these are the methods that are called often, so we only have to compile these. And this small method calls another small method, so we can inline it. So it's way better at optimizing your code. So I've had cases in, like Rubinius has a lot of stuff written in Ruby itself. So if I have cases where I improve performance by introducing a new method, which is sometimes people are confused by that, but it actually was a method that ran some code for a fallback case. And because of that, because I extracted that fallback case into a separate method, it would not optimize and compile that fallback code because it was almost never used. So it actually could optimize the remaining code better because it would just ignore the fallback case. And there's another important thing, write proper benchmarking. So if you want to be able to say, this is slow, please benchmark it. If you run Ruby, if you want to try Rubinius, and you think, oh, my application is really slow, please show us, because I'm sure we can optimize things either in Rubinius or your code, or have ideas, okay, how can you approach this idea better, and how can you fix this problem? So, short recap. So, a fast dynamic language is not, it's just harder to make. It's just not impossible. So there's no really fundamental property there that should make it slow. A lot of people sometimes they say, oh, we got to rewrite this in C because it's faster. What they don't realize is that when they rewrite it in C, it's also a refactor. So they change the way they approach the problem. So they approach it in a far more sensible way from a performance perspective. So then they say, oh yeah, we rewrote it in C and now it's 20 times faster. Yeah, okay, but you also changed the complete way you implemented it, and it might be very possible to do that differently if you also just kept using a dynamic language. Although there are APIs in dynamic languages that are really useful to add, so make sure you don't have to copy data all the time and things like that. And the second thing is, please write simple and well-factored code, and it's often easy to optimize for a virtual machine in that case. So, are there any questions because of what I told, or everybody's like, oh yeah, fine, whatever? You have a question?
Pointer optimization there, saying that only an address divided by 4 is a pointer.
Right.
So you're not optimizing for variables less than 4 bytes.
The thing is, what's behind that is it's called alignment. So for example, I've been working on supporting ARM as an architecture, and we use compare and swap operations a lot because we use concurrent things. And compare and swap on ARM, you always have to do that on what's called aligned memory. So if you want to compare and swap a 64-bit value, it always has to be on a boundary of 64-bit values. So, and on 32-bit, it's always aligned at least to 4 bytes, because we don't compact that further because it actually causes other issues like certain instructions suddenly causing illegal instruction sec faults, for example. So that I don't know if that answers your.
So you don't have an optimization for smaller types than 4 bytes. You don't suppose Boolean as storing as 1 byte.
No. Booleans are also literal. Like we store, like I talked about fixed like numbers. We store them as a single word size value. We also store, like in Ruby, nil, true, false as a single word sized value. It would actually be really hard to do that differently because it would change a lot of fundamentals, and you would actually get issues if you have an array with Booleans, because it would be different in size compared to other types.
Is there any recent data on a language like Ruby as opposed to a language like Java on the server? I get asked by clients a lot. They say, I'm a big advocate of Ruby. They say, I hear Ruby is slow. Everyone's heard the rumor from 10 years ago that Ruby is slow.
Yeah.
I do a lot of hand waving. I talk about Memcache and about Spark building, things like that. But at the end of the day, is there something I can point to them and say, 10 years ago it was slower and now
Yeah, well, 10 years ago, if you look at benchmarks from 10 years ago, I'm sure that for almost like a lot of benchmarks that it's way faster now. It's really hard to give hard numbers if it's not on a specific use case. But yeah, we've seen, like, if you compare it to what Ruby like 1.9 or 2.0 performance is right now, certain benchmarks on Rubinius are sometimes even 10 times faster, especially around like numerical calculations. We really optimize those pretty well. But there's other cases where the performance is pretty similar to what Ruby is. But if you compare Ruby 1.8 to 1.9 performance, that was a huge improvement. So yeah, a lot of the Ruby is slow stories came from the 1.8 days when it was actually pretty slow. Excuse me, what was the beginning of the question? I think there are plenty of good reasons for different use cases. Personally, I've done Java development as well, and I really hated like web style development in Java. That's really painful. It has a lot of ceremonial boilerplate code and all that kind of stuff. You have to write 100 lines to get 10 lines of functionality often. At least my experience with that, and that's way different with Ruby, so you can actually focus on the actual problem you're trying to solve instead of doing another thing. So actually it's really funny because I talked to Eric from Basher last night, and he talked about how he got into Ruby because of a book, and the book was called Generating Code with Ruby. So what he did at that point, he was a Java developer, and he generated code, like generated Java code, like the whole I need to create an entity bean with a database layer object and all that kind of stuff. He generated that code with Ruby code because he didn't want to write it every time himself. So that's definitely an advantage I see of using Ruby or also Python or whatever over like Java enterprise style stuff. But there's also cases where Java is fine. Yeah, last Java project I worked on has like the biggest class was 200 lines of code. So then it's manageable.
Do you have a question about Rubinius? In the wild, people are using it?
Yeah, for example, we're working with, I'm doing some software engineer out there, working with some of their customers who want to move over. There are people who are running it in production for like Sidekick applications where they really want to make use of the actual concurrency. So actually, because Sidekick, I don't know if you know Sidekick. It uses Ruby. It uses threads on Ruby. So if you do anything that's somewhat computational, then using Rubinius can really help because actually you can use way more of your system than just having a single process that uses like 100% CPU and MRI. Well, JRuby is also a lot better there because it uses a JVM, which also does not have like a global interpreter lock and those kinds of things. So it really depends. Like Rubinius really tries to be a drop-in replacement for MRI. So we support almost all the C extensions and almost all that kind of stuff. So if you want to move a application from MRI to Rubinius, it's usually easier than to move to JRuby. Oh, one last question or? Okay, one last question. Ideally, like for a lot of apps, it's just remove your gemfile.log, run bundle in Rubinius, and run. That's our goal. And for a lot of applications, that works. If it doesn't work for your application, we'd love to know about it and fix it. So that's very basically, and you know, always you have to things to consider if you run an application. Like, did you ever think of thread safety? Like in MRI, you can get away with a lot of things that in Rubinius you can't. But if you just use a Rails app, you very often don't use any global state except for Rails caching, which is actually thread safe. Not yet, but what? No, refinements, no. Refinements are still experimental in Ruby 2.0. If you want to know my opinion on refinements, come talk to me later because I have a fairly strong opinion on refinements. Let's say it like that. But yeah, we will add certainly like keyword arguments and that kind of stuff in the future. So, but I heard time was up, so thank you all for listening.